So now let's move over to this model, okay? And so you notice here, the linear form is this natural log versus time, which gives us a straight line. But here what I've got plotted, okay? So I just said call A0 1 molar and B0 0 molar, okay? And then what we get now, so really I'm looking at like this version. Even though I'm starting at 1 molar, it looks like it's, you know, the relative version. But now if you look at the profile for A, that's an exponential decay. So first order reactions are exponential decays, okay? So now what about the rate law for the product, okay? Well, I said up here, right, if I was really interested in, let's say dB by dt, right, that's just going to be positive K times A. We still think of it in terms of the reactant when I write the rate law. It's all about the reactants. Now, where did the positive come from? Well, because we recognize that B will have a positive 1 stoichiometric coefficient, right? So that's where if I know the reactant is dA dt equals negative Ka, and I have this simple reaction, the simple first order A goes to B, then the rate law of the product is just going to be dB by dt equals positive K still times A. Because in rate laws, it's all about the reactants. So let's check out my lines of code here. Okay, so I gave you these lines of code, but I'm going to show you where these come from. Okay, so ND-solve is the numerical solution to the differential equation. We didn't need the numerical solution here because you can see we got this very nice, simple exponential relationship. However, the numerical solution will still give us the correct answer. And when the reactions get more complicated, we don't get a perfect equation like this. We have to solve numerically, okay? So now what I have, so that's what that ND means, numerical differential solve. And look, A prime T. Well, that A prime T is the same thing as dA by dt, right? And now notice I use the double equal sign. And I use the double equal sign because I want a numerical solution, not a function solution. So that's why I'm not using that colon equal sign to give me the hard function. I want this to be like a solve the right-hand side of the equation based on the left-hand side of the equation. That's what the double equal sign means. Okay, so now you notice here, it's just negative K times A of T. So here I just wrote a bracket, but that's why I wrote it up here like this. So I'll write it in the same way I wrote my Mathematica, right? It's A prime of T equals negative K times A of T, right? It's the same thing as this, okay? So that's this line, all right? A prime of T equals negative K times A of T. And then look, now we can do it for B. And look, B prime of T is going to equal positive K times A of T, just like we came up with here, okay? And now other conditions that we have to put in, still the double equal sign because we're doing this numerical solve. We're saying call the initial concentration, so the concentration of A when T equals 0, we're saying call it 1 molar. We're saying B at time 0 equals 0 molar. And then now this is going to solve the solutions for A and B over this total time window that I set up right here. All right? And so now when I go to evaluate that model, before I can plot it, first it has to be evaluated. And I'm going to evaluate it for the concentration of A at time t, and I'm also going to evaluate it for the concentration of B at time t. And now look, these are all codes that we've used before. So I called this entire line here that I've highlighted Model 1. That's Model 1. So now look at my syntax here, okay? I'm saying plot, evaluate this list just A and B. If we had more reactants, maybe reactant C, reactant D, reactant E, etc., I would include those in the list. And now we remember that this means replace. And so I'm saying replace these solutions with model 1. And model 1 is right there. Okay? And now I say plot from t equals 0 to 5, plot range all, and then beautiful, we can see reactant decay, product evolution. And now what I've done to highlight the role of the rate constant, and this is extra. You don't have to do this in your model. But what I did here now was created a manipulate model for this first order reaction. And if you follow my hierarchy here, it's manipulate, plot, evaluate, right? These solutions. But now what I did was, instead of putting in model 1, so see, notice here, I do replace and then replace with model 1. So instead of doing that, I just say replace, and then I just recopied that entire model 1 code, which takes me all the way up to there. So that's the same thing as saying model 1, but now it goes comma, and I'm going to say let k be manipulated from 0 to 5, and my units here are inverse minutes. Okay? So now this is pretty cool. I love this. This is what I love about this Kinetica model. So now I have the rate constant turned off. And so to do that, right, don't forget to push that positive sign. So the rate constant's at 0. So you can see A is just over the 5 minutes, not reacting at all. But now this is really cool. As I increase the rate constant, you can see a bigger rate constant owes to a faster reaction. And look, if I take that all the way up to 5 1/minutes for the value of that rate constant, which I'm going to be talking about these units soon here, okay? Then you can see the reaction is over with very fast, right? And once A is reacted away, then B gets the corresponding correct stoichiometry, right? Now the concentration of B is 1.0. And once again, just to see that, if I slow the reaction down by decreasing the value of the rate constant, then the reaction takes longer to complete. So at that point now, I made the rate constant about 1/5 as much, and it takes about 5 times longer for the reaction to go.